Hello everyone, my name is Ritvik Rustagi and I am the owner of TMAS Academy. Today we'll be doing AP Physics 1 Unit 5 Momentum and Collisions. Now if you haven't already, please go to the description right now and get the free AP Physics 1 book that I wrote. That book has hundreds of examples and problems and free response questions with detailed solutions. And I believe that it has everything you need to know to get a 5 and an A in your class. So now, let's get started. So what is momentum? Well, the momentum it's denoted by p, lowercase p, and the formula for it is mass times velocity, or mv. The momentum of a system is defined as the sum of the momentums of each object in that system. And then direction is crucial for momentum problems because we're looking at velocity. We do mass times velocity. So it's very important to specify if it's positive, which means it's in the right direction, or if it's negative, which means it's in the left direction. So now as you can see, there's two blocks, one of 2 kilograms, one of 4 kilograms, and one moves at 3 meters per second, while the other moves at 4 meters per second. So what is the momentum of this system? So all we do is we multiply each individual mass to its corresponding velocity. And we do this for all the masses and we sum it up. So now for this problem, 2 kilograms times 3 meters per second plus 4 kilograms times 4 meters per second. That gives us 6 plus 16, which is 22 kilometers times meters per second. Now impulse. The change in momentum is known as impulse. Now impulse is also equivalent to the product of force times time. So delta P, which is change in momentum, or also known as impulse, that's equivalent to force times time. So now that brings us to the question, what is the area under a force-time graph? Well, it's impulse or change in momentum. Both are the same things, by the way. So now it's time for conservation of momentum. In a collision, linear momentum of that system will be conserved. In AP Physics conservation of momentum problems, you should write out an equation which shows the sum of all initial momentums in that system and equating it to the sum of all final momentums of that system. Now writing an equation out like this will not only reduce your chances of making an error, but it will also make the problem a lot easier to solve. Now, if there are external forces on a system, will momentum still be conserved? The answer is no. Momentum is only conserved when the net external force is 0. Now there's two types of collisions that we must be familiar with, an elastic collision and an inelastic collision. So in an elastic collision, momentum will be conserved, but kinetic energy will also be conserved. So that means not only do we have the equation for conservation of momentum, but we can also write an equation to conserve kinetic energy if needed. But for an inelastic collision, kinetic energy is not conserved, but momentum will still be conserved. Now, it's very important to be able to identify if a collision is elastic or inelastic if it's not given in the problem. Now, many problems will involve two objects that collide and move together after collision. And whenever they move together after collision, you have an inelastic collision. And in AP Physics 1 problems, if two objects don't stick together, then it is often an elastic collision. But if you want to verify that, then you must conserve kinetic energy. If the final kinetic energy equals to the initial kinetic energy, then it's indeed an elastic collision. But if they're both not the same, then it's an inelastic collision. And remember, for inelastic collisions, since both objects move together after collision, if that's the case, then when we're writing the conservation of momentum equation, we can use the same variable to represent final velocity. That's very important. For example, in the equation I showed before, the final momentum was represented as m1 times v1f, which means the final velocity of that m1, plus m2 times the final velocity of m2. But if we know they moved together, then the final velocity is the same, so we can just use v of f with the subscript of f. That donates the same common final velocity. Now, 2D momentum problems are rare, but it is worth knowing just in case. For such problems, you must conserve momentum separately in the x and y directions. Now, how would you do this? Well, you find the horizontal and vertical components of velocity and conserve momentum separately in each direction. In simple words, if momentum is conserved in a 2D problem, then it must also be conserved alone in the x direction and alone in the y direction. So let's start with some free response questions. Two identical objects, A and B, of mass m, move on a one-dimensional horizontal air track. Object B initially moves to the right with speed v0, and object A initially moves to the right with speed 3v0, so that it collides with object B. Friction is negligible. Express your answers to the following in terms of m and v0. So part A is determine the total momentum of the system of the two objects. So we already know that momentum is the sum of the product of mass and velocity for every object that we have. We multiply each mass's like velocity and like its mass, and we sum it up. So in this case, one mass is m and it has a velocity of 3v0. The other mass is m and it has a velocity v0. So we multiply m to 3v0, which gives us that one object's momentum is 3mv0 and the other object's momentum is mv0. We sum it up to get that the total momentum is 4mv0. Part B is a student predicts that the collision will be totally inelastic, which means that the objects stick together. Now, assuming this is true, determine the following for the two objects immediately after the collision: the speed and the direction of motion. So now, we will first find the speed. So since there are no net external forces, momentum is conserved, which means that initial momentum equals final momentum. And then we just use our equation for conservation of momentum. We multiply each mass's initial velocity to its mass, we sum it up, and then we find the final velocities, and we multiply to the mass, and we sum it up. We already know that initial momentum is 4mv0. Now, final momentum can simply be written as the sum of the two masses times final velocity, and the reason is that the final velocity is the same for both because they move together. So we can use the same variable to denote final velocity for both masses. So that means final momentum will be 2m times the final velocity. We divide 2m from both sides to find that final velocity is 2v0. And clearly, since this final velocity is positive, both masses move to the right. Part C. When the experiment is performed, the student is surprised to observe that the objects separate after the collision and that object B subsequently moves to the right with the speed 2.5 v0. So determine the following for object A immediately after the collision: the speed and the direction of motion. So again, this is a collision. So final momentum equals initial momentum. But we already found in part A that the initial momentum of the system is 4m v0. Final momentum can be written as m times va, which is the final velocity of that mass A, plus m times vb, and then vb will be the final velocity of block B. We equate the initial and the final momentums And after equating them, we get 4mv naught equals mva plus mvb. We divide both sides by m to get 4v naught equals va plus vb. We're already given that the final velocity of block B is 2.5 v naught. So we substitute that in. And now we subtract both sides by 2.5 v naught to find that va equals to 1.5 v naught. And since the velocity is positive, block A moves to the right. Now part D is determine the kinetic energy dissipated in the actual experiment. So we're now supposed to find the kinetic energy that is lost, which is simply the change in kinetic energy. So we'll find the final kinetic energy and the initial kinetic energy. So we know that kinetic energy in general is 1/2 mv squared. So to find the final kinetic energy of the system, we add up the individual kinetic energies of the two blocks. So for the block, that is for block B, that kinetic energy will be 1/2 times m, which is the mass, times 2.5 v naught, all of it squared, because that's the velocity. And similarly for the block A, it will be 1/2 times m times 1.5 v naught squared. And then we find initial kinetic energy, which is 1/2 m times 3 v naught squared plus 1/2 m times v naught squared. And then we can find that the final kinetic energy is 4.25 m v naught squared. The initial kinetic energy is 5 m v naught squared. And we subtract both to get that the kinetic energy lost is 0.75 m v naught squared. Now, the second free response. A block of mass m is resting on a horizontal frictionless table and is attached as shown above to a relaxed spring of spring constant K. A second block of mass 2m and initial velocity v naught collides with and sticks to the first block. Develop an expression for the following quantities in terms of m, k, which is the spring constant, and v naught. So we're supposed to find v, the speed of the blocks immediately after collision. And then part B is to find x, which is the maximum distance the spring is compressed. So in this problem, if we think about it, right when the mass of 2m collides with the mass of m, that's the point when momentum will be conserved. But once they collide, they both will stick together and act like an object of mass 3m with some velocity. And that kinetic energy that they both have will cause the spring to compress to some certain maximum distance. It compresses until kinetic energy is 0, which means all the kinetic energy after the collision, be very careful, not before the collision. The kinetic energy after the collision will convert to spring potential energy. So now let's start with part A. So for part A, we conserve momentum. We know that initial momentum equals to final momentum. So we write out our equation for conservation of momentum. The initial momentum is 2m v naught. And since they both move together after collision, we can denote the final velocity with the same variable v of f. And then we sum up the masses to find the final momentum. So 2m plus m times v final, that's the final momentum. We equate both to each other. We divide both sides by 3m to find that the final velocity is 2v naught over 3. And now for part B. We know that by the conservation of energy, the initial kinetic energy plus the initial potential energy equals final kinetic energy plus final potential energy. So the initial point that we consider is not the point before collision. It's right when the collision happens, at that exact moment of collision. That is the initial point. And the final position we consider will be the point when the spring is compressed to a maximum distance, which means kinetic energy is 0 at that point. And also, initial potential energy will also be 0, because that's right when the two blocks collide and the spring is not compressed. So that means the initial kinetic energy is 1/2 times 2m plus m. The reason why I wrote it like this is because after collision, both blocks stick together and act like one object of a larger mass, and this equals to 1/2 kx squared. We plug in our velocity that we found in the last part, 2v0 over 3. And then we can simplify to get 2m v0 squared over 3 equals to 1/2 kx squared. We multiply both sides by 2 and divide it by the spring constant k to find that x squared equals to 4m v0 squared over 3k. Now we take the square root of both sides to get that x equals to 2v0 times the square root of m over 3k. Now thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams such as the AP exams. And also, don't forget to follow the Instagram if you have Instagram to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.